Great. So thank you. Welcome, everyone. It's a great pleasure to have Shota Komatsu from CERN, who will talk about non-invertible symmetries, anomalies, and scattering amplitudes. Please take it away.
Okay. Thank you, Sakura, for introduction, and thank you for inviting me to speak. So yes, today I'm going to talk about this paper we put out like 2 or 3 weeks ago, which was done together with Christian Coppetti, who is a postdoc at Oxford, and Lucia Cordova, who is a postdoc at CERN. So the topic of my talk is about non-invertible symmetries, anomalies, and scattering amplitudes. And I'm also going to mention this paper, which appeared around the same time by Clay and Diego and Nicholas. There is no overlap between about the contents of these two papers, but like both papers discuss basically the same physical theory, the same RG flow. So I will also make some comments about this as well. Okay, so let's start. Oops. Okay, so I guess like for this audience, I don't need to emphasize, but let me just still emphasize that the symmetries and anomalies are fundamental concepts in theoretical physics. And one important use of symmetries and anomalies are they constrain the renormalization group flows. For example, thanks to the Tofut anomaly matching, you can sometimes know that certain terms in the low energy effective Lagrangian should be there because of the anomaly matching. And using the symmetry, sometimes you can argue that the certain terms in the Lagrangian cannot be generated by the renormalization group flows. And of course, they are not just theoretical concepts. They are also relevant for actual experimental physics, like collider experiments. So I thought I should mention the word collider because I work at CERN. What I mean by collider experiments are more or less synonymous to scattering amplitudes in the context of like a computing well, from the theoretical point of view. And as we know that the symmetry provided the organizing principles for particles and resonances that you see in the collider experiments, and the approximate degeneracy or approximate patterns of particle and resonances, for example, mesons, actually provided an important hint about understanding the theory behind. And also, historically, anomaly also played an important role. For example, ABJ anomaly was necessary for explaining experimentally observed processes, for example, pi0 to 2 gamma decay. And nowadays, there is a variety of like a generalization and refinements of these anomalies and symmetries. For example, there are higher form symmetry, non-invertible symmetry, two group and higher group symmetries, and also mixed anomalies and discrete non-perturbative or global anomalies. And so here the reference is pretty much incomplete. Well, it's really impossible to list all the references. So I just like listed some of them. Let me just apologize for those whose works are not included, but yeah, but no offense. Okay, so now, however, like unlike the traditional like symmetries and anomaly, like ABJ anomaly, it is less explored. What is the implication of these like modern symmetries anomalies on scattering amplitudes? And so that is the question that I want to address. Like that's a kind of big question that I want to discuss in this talk. And I'm going to, the punchline of the talk is that in the presence of certain non-invertible symmetry or anomalies, the crossing symmetry of the S matrix is modified. So that's the punchline of the talk. So the crossing symmetry basically means that you can view this scattering process, like a scattering between a red particle and a black particle, in this way or in this way. And if you exchange like a certain kinematical variable, which are often called Mandelstam variables. And normally, like they, after doing the appropriate exchange of labels, they are basically equal if you also swap the kinematical variables. But what we found is that that's not the case in the presence of certain non-invertible symmetries or anomalies. So let me just right away say what I mean by certain. So in this talk, I'm going to focus on RG flows to gapped phases in 1+1 dimensions. I will make some comments about higher D at the end, but not very concrete. And for the discussion, I'm going to study and focus on integrable flows, because in those flows, you can actually know what the exact S matrix at the non-perturbative level is. And that was important for us to check the claim. But as you can see later, the argument actually applies to non-integrable theories as well. Okay, with that, so this is the plan of the talk. So first, I'm going to give you a brief introduction and a recap of the non-invertible symmetries in 1+1 dimension. Then I'm going to talk about a particular RG flow that I would like to study, which is integrable flow from tree-critical Ising model, and then discuss its S matrix. And then I'm going to give the physical derivation or argument of the modified crossing rules. And then I end with the conclusion. Okay, so let's start with the non-invertible symmetry review. So by now, like we all know probably that the symmetry generators in QFT are basically like a D-1 dimensional topological operators. And because it's a topological operator, you can actually deform it in an arbitrary way. And in particular, you can move it in the time direction, and that basically amounts to a conservation of the charges. And in the case of 1+1 dimension, which is two-dimensional system, D-1 dimension means like it's one dimension. So that symmetry generators are basically line operators, topological line operators. And one important property, especially in the case of usual group-like symmetries, that they can be multiplied. So you can put two line operators on top of each other, and they fuse according to the group law. So here, like I'm imagining that the symmetry is a group-like symmetry, and the G, A, B, C are basically elements of the group. And however, we know that there are like actually generalization of this concept, which nowadays are called non-invertible symmetries. And in 1+1 dimensions, they are basically fully understood from a mathematical point of view, and it's called fusion category. And the difference from the usual group-like symmetry is that if you multiply the two objects, then you do not get a single object, but you get the sum of different objects. And this NABC is some non-negative integer called fusion coefficient. And this may sound exotic, but actually, like there is a very simple system which exhibits this non-invertible symmetry. This is a well-known model, which is the Ising model at criticality, or like people often call it Ising CFT. So this is all basic, but let me just review what the non-invertible symmetry of the Ising model is. So I'm talking about 2D Ising model on a lattice, and then discuss the continuum limit. And in particular, I'm imagining the Ising model on a square lattice. And as we learned in the StatMech course, this Ising model, depending on the temperature, are in the ordered phase or disordered phase. And then there is a critical temperature, TC, at which basically the theory long distance physics is described by conformal field theory. And I guess many people also learned that there is a thing called Kramers-Wanier duality, which basically maps the partition function and correlation function at low temperature to the correlation function and partition function at high temperature. And the relation is basically given by this. And so interesting point of this duality is that if you focus on a theory precisely at T equal TC, then this is a map between the same theory, whereas like if you are away from TC, then it's a map between a different theory. So therefore, at T equal TC, you can think of this as a Kramers-Wanier symmetry rather than duality. Okay. However, like this symmetry or duality has a little bit weird feature. What I mean by this is that if you think about these systems from the quantum field theory point of view, at high temperature, you only have, in the low energy, you only have one vacuum. So in the Landau-Ginzburg description, you have like this kind of potential and you only have one vacuum. Whereas in the low temperature, the symmetry is spontaneously broken and you have two vacuums. And as you can see, like this duality maps low temperature and high temperature. So this is actually 2-to-1 map. So there is a kernel in this map. And the precise map, you can work it out, and then it's given by this expression where plus is the vacuum here and minus is the vacuum here. And the map is like a plus is mapped to the 0, like the single vacuum here, and a minus is also mapped to single vacuum, whereas the single vacuum here is mapped to the linear combination. And as you can see, this is non-invertible because if you consider some linear combination like plus minus minus, then it gets annihilated under the duality transformation. So this weird feature carries over also at T-co-TC, and this can be summarized as a this kind of fusion category, which is often called Z2 Tambara-Yamagami category, and which satisfies these fusion rules, like where eta is a Z2 symmetry and N is a Kramers-Wanier symmetry. And you can actually check that this fusion rule is consistent with this map. And however, in order to study the S matrix, we need to consider RG flow to massive series because the CFT, precisely speaking, doesn't have a well-defined S matrix. So for that purpose, actually 2D Ising CFT is not very good because whatever perturbation you do, Kramers-Wanier symmetry is actually always broken by relevant perturbations. And that's of course clear from here that because if you do the temperature perturbation, then the Kramers-Wanier symmetry is not a symmetry, but it becomes a duality. And then you can ask, what is the simplest or simple RG flow preserving this Kramers-Wanier duality symmetry, Kramers-Wanier symmetry? And for that, you don't actually need to look very far. So for that, you just need to notice that Ising CFT is the simplest unitary minimal model, M3,4. And as soon as you look at the next simplest one, which is called tricritical Ising CFT, you find the flow, RG flow, which preserved the symmetry. And so this flow was very much well understood. So if you start from the critical Ising CFT and perturb it by what's called phi 1,3 operator, whose dimension is, I think, 6/5, then it flows to, and if you perturb it by the plus sign, positive sign, it is known that it flows to Ising CFT. So here, IR is still CFT. And so you cannot really define the S matrix in the usual sense. Well, actually, technically speaking, you can still define it because Ising CFT is almost like a free series, but it's not what I'm going to talk about today. But it is also known that if you flip the sign of perturbation, it is known that the tricritical Ising model flows to the gapped phase with 3 vacua. And this was studied using a conformal perturbation theory or a continuum limit of the lattice model and also various integrability approaches. And let me also just say that you can continue doing this. Starting from Ising model, you can also perturb the Ising model of phi 1,3 of the Ising model, which is actually nothing but the temperature perturbation I just described. If I start with Ising and then do this perturbation with a plus sign, you get this single vacuum, and with minus sign, you get this vacuum with 2 degeneracy. Okay, so this is a kind of general phase diagram. Starting from the RG flow diagram, starting from the tricritical Ising model. And let me just explain a bit more detail okay, so one thing I should emphasize is that this flow, these 2 flows, starting from tricritical Ising model, preserves the non-invertible symmetry, Kramers-Wanier symmetry. So let me now explain how the non-invertible symmetry acts on these 3 vacua that you see in the IR. And so the Z2 defect, eta, basically just exchanges left vacuum and the right vacuum. So, and then does nothing to 0. It leaves 0 invariant, middle vacuum invariant. Whereas N defect basically maps the middle vacuum to a linear combination of the left vacuum and the right vacuum. Whereas if you act N to the left vacuum or right vacuum, you get 0, the middle vacuum. So this is kind of a bit analogous to what I explained a few slides back about how the Kramers-Wanier duality acts on the Ising model perturbed by temperature. So in some sense, this vacua can be understood as a kind of a superposition of disordered and ordered vacua in Ising model. Well, just from the point of view of how the symmetry acts. Okay. And so let me also make some remark about this flow. So here I said there are 3 vacua in the IR, but 3 is actually the minimal number of vacua allowed by the non-invertible symmetry. So as soon as you know that this flow preserves the Kramers-Wanier or Z2-Tambari-Yamagami symmetry, you can immediately say that having a single vacuum is not allowed, because you need to have some representation of these symmetry lines for which all the entries are basically like non-negative integers. And you cannot, okay, this must be 1 and this must be 1. Actually, there is some typo about the eta, action of the eta. And that's because like all the entries need to be non-negative integers. And you can check that using these matrices, like this non-invertible symmetry algebra is realized. And you can also go high up in the minimal model indices, and this pattern actually persists. What I mean by that is that if you start from the minimal model, nth minimal model, and then perturb it by phi 1, 3 with positive sign, you get next minimal model n minus 1 comma n. Whereas if you perturb it by negative sign, you flow to the gapped phase with n minus 1 vacua. Okay, any questions so far? So now let's continue. So now let me discuss a bit more in detail about the flow from critical Ising model and then its S matrix. So as I said, what I'm going to study is this flow starting from the critical Ising model perturbed by minus 1, 3, and then going to the 3 vacuum. And so this flow actually has a nice property that it preserves integrability. So at the UDP fixed point, which is basically just a critical Ising model, there exist infinitely many mutually commuting higher spin charges. That's just because of the consequence of the Virasoro symmetry. And it was shown by Zamolodchikov that perturbation of this CFT by phi 1, 3 or phi 2, 1 or phi 1, 2 all preserve higher these mutually commuting higher spin charges. So this is just basically like a straightforward exercise of which of these operators commute with these higher spin charges. And now, once we know that there are infinitely higher spin charges conserved along the flow, and then you can immediately argue using the argument by Shanker and Witten that multiparticle S matrix needs to factorize into a product of 2, 2, 2 S matrices. And furthermore, 2, 2, 2 S matrices need to satisfy the consistency condition called the Yang-Baxter equation. And furthermore, Zamolodchikov basically used the unitarity crossing and this Yang-Baxter equation as an input and basically determined the exact form of the S matrix basically almost uniquely, just imposing the consistency conditions. So now let me just give you more detail about the S matrix determined by Zamolodchikov. So, in order to determine the S matrix, I first need to talk about particles that we are scattering. So in this flow, particles in the IR are basically kinks interpolating adjacent vacua. So here I switched the notation. So previously I was expressing this vacuum plus and this vacuum minus and this vacuum 0. But to make it consistent with the notation in literature, from now on, I'm going to denote this vacuum 0 and this vacuum 1/2 and this vacuum 1. So, and the important point is that the kinks interpolate between adjacent vacua. So this configuration is allowed, but you cannot put 0 and 1 here, for instance, because there are no stable particle like that. And of course, like because we are also discussing the S matrix, it also depends on kinematical variable. And in 1 + 1 dimension, in higher than 2 dimensions, if you consider 2, 2, 2 scattering, there are like a 2 Mandelstam variable S and T. But in 1 + 1 dimension, you only have 1 Mandelstam variable, which is S, which I decided to parameterize using what's called rapidity variable theta. And M is the mass. So in summary, S matrix has basically 5 arguments, these A, B, C, D are basically labeling for vacua. And then this theta is basically Mandelstam variable. And then theta, you can also think of it as a difference of the rapidity of the two particles. And because of this relation, the Mandelstam T is not independent from S, and it's given by this expression. And on top of it, Zamolodchikov imposed the crossing and unitarity. And in this kink scattering picture, crossing symmetry is given by this expression. So here, so basically crossing means that you either view this S matrix in this way or in this way. And if you want to view it in this way, which is just the picture here, then you need to swap S and T. In the rapidity variable, that amounts to exchanging theta with I pi minus theta. And whereas unitarity is basically, because this theory is integrable, there is no multi-particle production. So the two-particle S matrix need to saturate the unitarity. So S times S dagger is just 1. And together with the Yang-Baxter equation, which now takes this form because of the kink scattering, Zamolodchikov basically fixed the S matrix uniquely up to what's called overall CDD factor, which is not very important in our discussion here, in the following way. So that this is basically the form of the S matrix Zamolodchikov determined, and this is some complicated factor that's needed to ensure the unitarity. And the important point here is that, as you can see, the expression inside a square bracket is rather simple, but it is not crossing symmetric, because if you do the theta going to I pi minus theta, there is a difference of the factor. So in order to remedy that difference, Zamolodchikov basically multiplied this additional factor, which is the ratio of these to the power I theta over 2 pi. So here I didn't explain the notation, but here in the case of trig critical model, n is 3, and then these are given by 1. D0, D1 is 1, and then D1 half is square root of 2. So A, B, C, D runs from 0, 1 half, and 1. Okay, and so at this point, I don't need to mention this, but let me just mention that these are basically quantum dimensions. And of course, because we also know that this flow preserves the non-invertible symmetry, so we expect that this S matrix should commute with the action of the non-invertible symmetry. So this is the first thing we checked when we started this project. And the consequence, the result was a little bit surprising. So we basically just took this Zamolodchikov S matrix and checked whether this commutes with eta defect and n defect. And what we found is that it does commute with the eta, which is Z2 symmetry, but it actually doesn't commute with the action of the Karamas-1A duality symmetry. And then Karamas-1A duality word identity is given by this kind of expression, which says that a single S matrix element is equal to the sum of the S matrix element, and you can explicitly take this expression and check that it's not satisfies here. So this is a kind of paradox, because what we are seeing is that the following 4 properties that one would postulate for this S matrix or for this theory are mutually incompatible. So the first is the unitarity, and the second is crossing, and the third is integrability. Well, technically it means Yang-Baxter equation, and the fourth is the non-invertible symmetry. So to resolve this paradox, we need to give up at least one of the 4 properties. So the question now is which one we should give up. Certainly, we should not give up unitarity because it's a kind of basic principle, and there is no indication that this flow leads to some non-unitary theory. And what about integrability and non-invertible symmetry? So the presence of those symmetry, like a higher spin symmetries and the non-invertible symmetries, are rather established facts, because you can check it near the UV fixed point by checking whether the deformation operator commutes with these symmetry generators, and they do commute. So we cannot give up these conditions either. And that basically means that the only viable option is to give up crossing symmetry. Okay. And in fact, we found actually the S matrix, which is a small modifications of the homological S matrix, which satisfies 3 of the 4 properties, but not crossing. So this is basically given by this expression. As you can see, it's a very like a simple modification. So this is the homological one, and this is our proposal. And we just dropped this I theta over 2 pi part, because this is precisely the part which was screwing up this identity. And you can actually check that this S matrix satisfies unitarity and then non-invertible symmetry, and also the Yang-Baxter equation. And of course, there is a price to pay. The price is that like now the crossing symmetry is not, the usual crossing symmetry is not satisfied, and it gets modified. It gets modified by precisely this factor that you see here. And of course, like this was slightly like an indirect argument that why about modified symmetry. And for the rest of my talk, I'm basically going to give you an explanation of what is the physical origin of this modified crossing rule. Okay, any questions so far? Good. So let me now also make some remarks. And so although like in my talk, I'm going to focus on this particular example, which is a flow from the tricritical Ising model, but this modified crossing, you can also see it in many other examples. That's what we found. So for example, you can see it in the phi 1,3 deformed higher minimal models, and also phi 2,1 deformed tricritical Ising model, which was also studied in the literature. And there is an interesting fact about this flow. And for this flow, well, actually this flow also preserves S integrability. And in the literature, there are 3 different proposals for the S matrix of this flow. One by Zamolodchikov, one by Klaas and Meltzer, and one by Musardo. And our analysis, especially like by checking the commutation relation with the non-invertible symmetry, supports the one by Musardo, and which does satisfy this modified crossing symmetry. And in the past, like people did notice that this amplitude by Musardo satisfies modified crossing symmetry, but there was not really a clear justification of why this had to be the case. So because of that, like people are not sure about like which one is actually the correct one. By the way, another thing I forgot to say is that this flow preserved a Fibonacci fusion category. And there is also another example we studied, which is the example with Z2 anomaly, which is actually JJ bar deformed SU2 level 1 versus Witten model. And there, by imposing various consistency, we found S matrix, which again obeys a modified rule. So this C is just a charge conjugation operator. But the important point here is that there is a minus sign. And as I explain a bit more later, this minus sign is basically the manifestation of the F symbol coming from the Z2 anomaly. Okay, so now I'm going to proceed to the derivation of the modified crossing rules if there are no further questions. Okay. So now let me provide some argument or physics derivation of this modified crossing rules. So the key physical input, there are 2 key physical inputs. So the first one is that in the IR, the action of a kink on vacua, you can view it's basically the same as the action of the symmetry line. So let me just explain a bit more about this point. So as I said, in this flow from the tricritical Ising model, so you have 3 vacua and the particles are kinks interpolating neighboring vacua. And so across the word line of the kinks, basically 0 can go to 1/2, and 1/2 can either go to 0 or 1. So this is precisely the same as the action of the symmetry line, because symmetry line n also maps 0 to 1/2 and 1/2 to 0 or 1, for a more precise linear combination of 0 and 1. So from the so therefore, from the like IRTQFT point of view, you can identify the word line of a kink with the word line of with the symmetry line n, which I denote by V in the following slides. And I should also emphasize that this is actually rather a strong assumption, the identification of kink with the action of the symmetry line, if we didn't know anything about the IR. For example, if you, I'm not going to explain the details of this, but if you consider the other flow that I mentioned, which is phi 2,1 deformation of the tricritical Ising model, and then declare that the word line of a kink is the same as the symmetry line, which in that case, like a symmetry line of the Fibonacci fusion category, which is W. This immediately implies that mass of the kink is the same as mass of the breezer. So in this deformation, the IR has two vacua, which are asymmetric. And then people know that there are like three kinds of stable particle, kink and an anti-kink, and a breezer, which is a fluctuation around this vacuum. And people also notice that like these three masses are exactly equal. But if you assume that like the particle, this kind of, well, okay, what I want to say is that this is, you can think of this as also a kind of consequence of this identification. As soon as you say that like the particle word line is the W line in the Fibonacci fusion category, then basically like a kink, anti-kink, and breezer kind of get identified. So therefore, it immediately follows that these masses are the same. But as you can see, physically, this is a very, very like a surprising consequence. But fortunately, as shown in this paper by these authors, this result, which basically says the mass of the kink is the same as the mass of the breezer, you can actually derive it from the by imposing a non-invertible symmetry and analyzing how it acts on the kink Hilbert space. And similarly, and extending that argument, you can also justify this assumption that you can view the word line of the kink as the word line of the symmetry line. Okay, so now, so another important key physical input is that in this flow in which you have like three different vacua, the vacua are basically in one-to-one correspondence with the symmetry lines. So, so the correspondence goes like this, like you identify this vacuum as the identity line, and the 1/2 vacuum with this n defect, and the one vacuum with the eta line. And so this is basically an alternative way of saying that like these vacua basically form a regular representation or like adjoint representation of the fusion category. So the action, how the vacua gets transformed under the action of the symmetry line is the same as like how you fuse the different two line defects. And as a trivial consequence of this, all the vacua, 0, 1/2, and 1, you can obtain them from 0, like the left vacuum, by acting symmetry lines. For example, if you act n to 0, then you get 1/2. And if you act eta to 0, then you get 1. So in this sense, like there is a close relationship between the vacua and the symmetry lines here. So those are important, two important physical inputs that I'm going to use in the following slides. Okay. So with this, let me start with some warm-up and about understanding how the symmetry line acts on the vacua. So let's first consider path integral of this QFT, this RG flow, on a large Euclidean disk with a boundary condition that the fields approach to the vacuum 0 at infinity. And so this basically, you can think of it as a kind of computing the norm of the vacuum 0. Sorry, the norm of the state whose like reach asymptote to 0 on both left and right infinity by cutting this circle here. And I'm going to normalize this state or path integral so that this becomes 1. So this just set the normalization. From more TQFT language, like I'm basically talking about the state in open Hilbert space with specified boundary condition. And as I said, because the vacua are in one-to-one correspondence in the flows that we analyzed, you can get other vacua by acting symmetry lines. So if you want to get like a vacua, then you start from this half circle, which define the state, and then act a symmetry line like this. However, there is one thing we need to take into account. So if you define the state like this and then compute the norm, now the norm is not 1 because there is a circle here, and the expectation value of the symmetry line, circular symmetry line, is given by what's called quantum dimension, and it's generally not 1. So when I talk about normalized, like the normalized state, then we need to divide this state by square root of d of a. Now, using the normalized state, which I normalize like this, and then let's discuss the matrix element of the symmetry line acting on this vacua between A and B. So I'm thinking about the action of the symmetry line phi. And because of this denominator, I get 1 over square root of dA and dB, and the rest is given by this expression. And a big circle just gives you 1 because of the normalization. So what you're left with is this network of lines. And using the identity of the fusion category, you can actually evaluate this network of line, and you see that up to this fusion coefficient, it gives square root of dA, dB, d phi. And if you use this and this, then you see that it doesn't just give you this fusion coefficient that is the usual action of the symmetry line, but it also gives you square root of d of phi. So this basically tells you that to correctly realize the symmetry algebra, we need to kind of divide this symmetry line by 1 over square root of d of phi to just pick up this piece. Okay. So this is a kind of like the correct symmetry line when you consider this open Hilbert space. So now let's consider, so far we were talking just about the vacuum, but now let's consider a state with a kink interpolating between A and B. As I said, the kink can be identified with the symmetry line from the IRTQFT point of view. So the state which has a kink interpolating between A and B looks like this. Now I can again compute the norm of this state, because if I like consider sandwich like a Brian cat, then again get this kind of expression, and this can be evaluated into this expression. So now we use the correctly normalized symmetry line, and also the correctly normalized state to compute the matrix elements between different single kink states. And that gives you this expression, and the most complicated part is given by this network of lines. So here we have like this V line because we are considering the state with kink, single kink, and this fine line is the action of the symmetry line. And importantly, like here, V and phi are not intersecting. So you should view it from the 3D point of view. And if you view it from the 3D point of view, this is nothing but a tetrahedron. And this gives you what's called tetrahedral symbol, which is just related to the F symbol. So this is the derivation of the matrix element between single kink states. And using this action, we basically check that our S matrix commutes with the non-invertible symmetry. So far, as I said, this was just a warm-up to get used to the notation. So now, but is there any questions so far? Okay. Now, let's now talk about the modified crossing for the S matrix. So before we get to the derivation, let me just summarize the key steps or like a key physical inputs. So basically, I'm going to show that the modified crossing can be derived using the following three properties. The first important property is that IR dynamics is described by a non-trivial topological quantum field theory. And basically, you can compute various expectation value of networks of lines using that. And the second important thing is that normalizations of in and out states that we use for the S matrix are corrected by this topological QFT degrees of freedom. And the third important point is that the corrections depend on the channel, S channel, T channels we consider. And this is the main reason why we get the modified S matrix. Okay, so now let's go through the derivation. So to discuss the S matrix, so we need to define S matrix first of all. So the textbook way of defining the S matrix is to use the LSZ reduction. So you compute the correlation function, and then you do the Fourier transformation, and you look at the poles of the correlation function and extract the S matrix. However, it is a bit unclear whether that approach is applicable here, because here we are scattering kinks, and generally kink creation operators are actually non-local operators. Or more precisely, like from the UV-CFT point of view, generally they are like in the twisted sector. And it is well, it might be possible to generalize the LSZ reduction formula, but at this point, I don't know like whether we expect the same analytic properties like the usual correlation function if you do the Fourier transformation. So therefore, we kind of decided to resort to an alternative approach, which does not involve like looking at the poles of the Fourier transformed correlation function, which is discussed in Isaacson-Zilber textbook of QFT in chapter 5. So this approach is similar to LSZ reduction, but it doesn't involve looking at the poles. So what they do is that you basically consider two Cauchy slices, past and future, and then insert some operator which creates a particle, and then basically take derivative with respect to the direction which is perpendicular to the Cauchy slice, and then convolute with the plane wave. And then finally, in the end, you take the limit in which like this separation T goes to infinity. And in the usual theory with Lagrangian description, you can actually show that this basically gives you the same S matrix that you get from the LSZ reduction. So you can show it in the perturbation theory. Again, in the case of kink scattering, there is not actually a proof, but we are kind of postulating that it also works here. And the reason why we prefer this method is that it doesn't involve looking at the poles of the S matrix. You can more or less directly define the S matrix starting from the correlation function. So we thought like it has a better chance of working. Okay, so strictly speaking, it's not really like a rigorous derivation, but let's see how far we can get with this. So in our case, as I said, we are going to scatter kinks. So basically what we need to compute is first consider some kind of like a disk partition function, Euclidean disk partition function with specified boundary condition and certain boundary condition changing operator inserted. That basically amounts to like inserting kink creation operator. And then you do the analytic continuation to Lorentzian spacetime, and then take the limit in which like this separation, this Lorentzian size of this analytically continued disk becomes infinite. However, in the process, we also need to take into account the normalization of in and out state. And generalizing our discussion about the action of the symmetry, two particle state would look like this from the IR TQFT point of view. And so this is an in state and this is an out state. And now using this TQFT expression, I can also compute a correction to the norm of the in state coming from the TQFT degrees of freedom. And that is given by this network of lines. So this is the in state and this is out state. Note that they are slightly different because like here we only have C and here we only have A. So this basically means that if you want to have an S matrix that can be multiplied like a usual matrix, we need to divide by this analytically continued correlation function with Fourier transformation by the square root of the norm. And the key point here is that numerator is basically analytically continued this correlation function, and it basically satisfies the usual crossing symmetry. You can either decompose it in this way or this S channel or T channel, and there is no subtlety. However, as you can see, that this denominator really depends on the choice of the channel. So here we have this kind of network of lines because we chose the S channel scattering. But if you chose T channel scattering, the line should go like horizontally inside the circle. And this is basically the key reason why we get the modified crossing. And more precisely, like because of this extra factor, which takes care of the normalization, we expect that if you do the crossing, you need to multiply this extra factor, which is basically given by the ratio, square root of the ratio of the norms of in-state and out-state in S channel and T channel. And you can check that this formula indeed reduces to the expression that I already gave by evaluating this network of line explicitly. And in the case of Z2 anomaly, the expression upstairs and expression downstairs are basically related by F move, and that's why we get additional minus sign. Okay, so now I'm already at the conclusion.
Shota,
yes.
Shota,
yes.
Sorry. About the Z2 case, sorry, can you just say a little bit more? So on the left, this is a square root of something, right? So how do you get a minus sign out of the square root?
So in the Z2 case, again, like the flow that we are studying is a kind of like regular representation of Z2 because in the IR we have two vacua. So the two vacua you can view it as an identity line or like a Z2 line. So what we are going to get is that, for example, in one configuration, I have, I guess you can see my cursor, right?
Yes, I can see.
So in one configuration, you have like this circle and also this circle, and then nothing for A and C. So let's imagine that D is the Z2 line, and D and B are Z2 line, and A and C are identity line. And whereas here, I get like a circle square already here. So, so the point here is that although it's inside a square root, like these two factors give basically the same network in the case of Z2. So it just amounts to the ratio of this and this without square root.
Oh, I see. So it's like a square root of -1 square, which you take to be
exactly.
-1.
Yeah, exactly.
But intuitively, I thought the issue here is about the normalization of the in and out state.
Right.
But the norm of a state is always positive. So just intuitively, I'm still a little bit confused about how we get a minus sign in the Z2 case.
I see. Okay. Right. That's, so it's true that we are kind of oversimplifying here because precisely speaking, in the case of Z2, we also have this charge conjugation matrix.
Right.
Because there is Komatsu degeneracy.
Right.
So it's a good point. Right, it's a good point. Yeah, probably all I can say right now is that we cannot just use this picture in that case. We have to be a bit more careful about thinking about the degeneracy.
Okay. Okay. Thank you.
Yes, Nat is also wants to ask.
Yeah. Can you explain how you measure this phase? Is this phase, this minus sign, is it measurable?
Oh, that's a good question. In some observable. Yeah, that's a good question. I don't have an answer now.
Because if the answer is no, you don't need to answer Shuheng's question.
That's also true. Yes. Let me think. Right. That's true. So the phase of S matrix, if you are, well, if you are thinking, if you consider something like cross section, of course, like we will not be able to detect it. But I guess generally speaking, like if you consider some kind of like for example, in higher D, like if you consider something like energy correlator, then like it can also more like a more complicated in observable, it can detect the phase, I think. But I don't know like how to precisely measure this phase in this setup.
The question is really whether there's a unitary transformation on the in Hilbert space that removes it.
Yeah. Right. Yeah, I see. Yeah, that's a good point. Yeah, I don't have an answer now. Yeah.
Thank you.
Okay, so let me just conclude. And so the conclusion is that in RG flows to gapped phases in 1+1 dimension, non-invertible symmetries and anomalies sometimes lead to modified crossing symmetry. And physically, it comes from corrections to the norms of in and out states, and due to the TQFT dynamics. And in particular, like in the cases of the RG flow from the critical Ising model, this is not even a phase, this is some number. And one comment I wanted to make is that similar modified crossing was already observed in Chern-Simon's matter theory in 2+1D. But I just like wrote the most recent paper by them. And but in their cases, like there was a Chern-Simon field already in the UV Lagrangian, and also it was kind of clear that the particle they are scattering are anyons, and it obeys some fractional statistics. So in our examples, at least in the derivation that I just gave, the braiding was not playing a crucial role. And in particular, like we expect that like this kind of modified crossing is there even in the general fusion category, not necessarily modular tensor category. And in general fusion category, there is no braiding. And another point to make is that in our example, it's just like a tricritical Ising model perturbed by phi 1,3. So in that sense, like a TQFT is more hidden from the point of view of UV description. So now let me just mention several possible future direction. One thing we are exploring right now is to do the S matrix bootstrap with no invertible symmetry, and possibly interesting target for this is a Harge fusion category, for which a field theory realization is not fully understood. And another point to make is that in this talk, I only focused on the flow to the gapped phase. But if you change the sign of the perturbation, there is a flow between minimal models. And I think it is not fully understood how the non-invertible symmetry acts. What is the consequence of non-invertible symmetry in these flows, especially along the RG flow. And the third point is that recently there are various people discussing the scattering of fermion against monopoles. And one of the feature they found is that like even if you initially scatter fermion, then like the final state is basically some kind of composite of fermion and monopole, which are connected by some non-invertible symmetry defect. But so this is a kind of S-channel monopole fermion channel. But if you imagine doing some kind of like a crossing transformation, this picture becomes this picture. But this picture doesn't make much sense because you cannot really like dress the out state with something in the past, which are monopoles. So this is more like a monopole, anti-monopole going to fermion, anti-fermion. So this probably suggests that there is some modified crossing also in this context. And it was indeed like discussed from the on-shell amplitude point of view by these people. And finally, this was already briefly mentioned in the paper by on the Chern-Simon matter theory, but in some sense, like this modified crossing and then the non-triviality of the IR-TKFT affecting the S matrix is you can think of it as a toy model for IR effects, like Fadeev-Kulish dressing due to the soft photons and gravitons in gravity and gauge theory. So it will be nice if there is something that we can learn from this. Okay, with this, let me end my talk.
Great, thanks very much for this nice talk. Other questions? Maybe I can start with a question. Could you go back to this Chern-Simon's, the scattering of anyons? So what is can you tell a little bit about what the modified crossing is in that case? What it depends on, this modification? Is it as explicit as what you've written down?
So they have expression. So in that case, like you are scattering, say SU and Chern-Simon coupled to fundamental fermion. And if you consider fermion, there are like several different channels, like because fundamental representation can fuse to several different representations. And they wrote down the explicit expression for the crossing for each component of the S matrix. So it's not, it's explicit, but it's not a single formula like this.
Do you know what this modification would depend on? In your case, essentially, it's the quantum dimensions for this.
Right. In their case, they depend both on N and K, basically Chern-Simon level and the rank.
I think if I recall correctly, was the topological spin. It was
the spin. Okay.
Yes.
That's what I would have thought too. Great, thanks. Any other questions? We already had lots of discussion at the end.
Can I ask something?
Sure.
Yes.
It's a technical question, but in this modified crossing equation, if we consider examples where some of the fusion coefficients are greater than 1, then would it be further modified? Because when you compute this network of topological lines, then there will be some choices to be made at the trivalent junctions.
Right. Yeah, that's a very good point. So I didn't explain that, but like we are like focusing on the case where this fusion coefficient is just 0 or 1. And indeed, we do expect like in general cases like this gets further modified. So we only look at some case, well, precisely speaking, we looked at the case in which the lines are unoriented and also the fusion coefficients are 0 or 1.
I see.
So even for the Z2 anomaly case, we kind of like treated lines to be unoriented, which is a little bit unphysical prescription, but something that one can do.
I see. Thank you.
Any other questions? If not, then I'll stop the recording. Let's thank Shota again